In this video, I'm going to talk you through the Gram Schmidt orthogonalization process. And the idea here is that we're going to create a basis consisting of vectors which are orthogonal to each other by eliminating redundancy. And to do this, we're going to go through each vector and subtract the projection of that vector onto all of the previous vectors that we've added to our new basis that we're creating from the existing basis. So the algorithm states that we have n linearly independent vectors, e1 through en, and we are given this from the beginning. So if you are given a set of vectors and you're not sure if they're linearly independent, you need to check that first. But once we have our linearly independent set, which could itself be a basis, then we're going to take that basis and generate this new set B prime, which consists of these vectors that make up an orthogonal basis. And the first step is to set e1 prime equal to e1. So the very first vector, whichever one you've designated as the first, is going to be the same in both of them. And then you're going to go through the remaining vectors in B. And for each of them, you're going to subtract the projection of that vector onto all of the previous e sub I prime vectors, or e sub k prime vectors, as it's stated here. And the idea, if we look at the first example here, we have these two vectors. So we've got 1, 0 and 1, 2. Well, if I plot the vector 1, 0, let's just draw a two-dimensional coordinate system here. 1, 0 is this vector. There's 1. And 1, 2, and this won't be a scale, but that's okay, is going to be this vector over here. Now, if I am using these two vectors to create another vector, let's say I want to create this vector that I'm dotting out here. We don't need to know exactly what its coordinates are, but if I want to take care of the x direction, the x component of this vector, well, then it's enough to simply have this first vector, the 1, 0 vector. And I can use the x component there to create the x component of the vector that we're trying to describe in terms of these other two vectors. I don't need the x component of the second vector. And then when we get to the y component, I don't need any y component from this vector, which is good because there isn't any. It's enough to have the y component from the second vector, the 1, 2. And if the first vector, the 0, 1, did have a y component to it, then I could look at just the y component from the second vector. And the idea with the Gram Schmidt orthogonalization process is that we're going to eliminate the part of this second vector. If I'm calling this e1 and this e2, I don't need the projection of this e2 vector down onto e1. Whatever part of e2 is in the direction of e1 is unnecessary. I just need the part of e2 that is perpendicular to e1. And these parts don't have to be parallel to the x or the y-axis. In this particular example, our e1 prime will be parallel to the x-axis, our e2 prime will be parallel to the y-axis. But given any two vectors, if I have a vector like this, a vector like so, then I don't need the part of the second vector that I drew that is parallel to the first one. I don't need this portion of it right here. I only need the portion of that vector which is perpendicular to the first one. So I only need this part of the second vector. So let's look up at the algorithm again. So we're going to start by setting e1 prime equal to e1. So if I call this e1 and e2, and for the sake of writing, I'm not going to put the arrows over my vectors here. I could write the e1 and the e2 like that, but I'm just going to leave those off for the sake of making this a little bit less messy. And then once we have our e1 prime, which is our same first vector, then e2 prime is going to be equal to e2. So we're going to take this vector 1, 2, and then we'll subtract the projection on to e1 prime of E2. And if we work through that in Mathematica, that projection, or you can work through it by hand, either way, you'll get that the projection is, well, even visually, we can see that the projection, the shadow that E2 casts down onto E1, or in the direction of E1, is going to be exactly E1 itself, because they both had that x component of 1 there. So this one works out very easily. And so our E2 prime is equal to just 0, 2. And if you were to check, and we can do that in just a minute, that the vectors in B prime, which are 1, 0 and 0, 2, each of the vectors in this set is going to be orthogonal to each of the other vectors in this set, and there's only one in there. So if we were to check that, take the dot product, 1, 0 dotted with 0, 2, that is equal to 0. So they are going to be orthogonal, perpendicular to each other, which is what we wanted. Now, once we have that basis, this is an orthogonal basis for the set. We can then create an orthonormal basis, if we would like, in which the vectors are all both orthogonal to each other and have length 1. So let's call that B prime sub, let's say, ON. And in this example, it's very easy to compute the magnitude. So the magnitude of this first vector, its norm, is equal to 1, so there's no change necessary there. The magnitude of the second vector is 2, so if I take that vector, divide by its norm, then we're going to end up with 0, 1. And here we get just the standard basis vectors. But in general, that doesn't necessarily have to be the case. So here is our orthonormal basis. Corresponding to this original basis that we started with, using Gram Schmidt to first create the orthogonal basis from that. The implementation of this in Mathematica is fairly straightforward. Let's just jump over there before we do the next example. We're going to define our two vectors. You can say v1 prime is just equal to v1. That's maybe even a better way of emphasizing what we're doing here. And you could run this in a loop when we have just two vectors, then there's not really a need to do that. We're going to take v2 prime, create that by taking v2 and subtracting the projection of v2 onto v1, and you can compute that using the projection command. So that is the 1, 0 that we saw earlier, and when we do the subtraction, it's a little bit out of order, then we end up with the 0, 2 that we got before, normalize that to make it length 1, and we get 0, 1. Now, we don't have to always normalize these. If we're not looking for an orthonormal basis, just an orthogonal basis, then it's fine to leave them as they are coming out of the Gram Schmidt algorithm. In the next example, we have three-dimensional vectors, and we'll just label these E1, E2, and E3 in the order in which they're listed in the set. And then our E1 prime is going to be equal to just E1. So there's no change there, 1, 1, negative 2. And then E2 prime is going to be equal to E2 minus the projection onto E1 prime of E2. That's the only term we'll have in the summation here. So that's the only projection that we need to subtract off. And that's going to be true in general. When you get to the second vector, there's just one projection that you're subtracting off to create the new E2 prime. Here, this is going to be equal to E2, the negative 2, 1, 2 that we have there. And the projection, you can find this using Mathematica or compute it by hand. We end up with negative 5/6, negative 5/6, and negative 5/3, which is equal to, we simplify all of that, negative 7/6, 11/6, and 1/3. Now, moving on to our last orthogonal basis vector, E3 prime. This is going to be equal to E3, and then we'll subtract the projection of E3 onto E1 prime. So whatever part of E3 points in the direction of E1 prime, we don't need that, so we take it off. And also subtract off the projection of E3 onto E2 prime. Again, whatever portion of E3 points in the same direction as E2 prime, we no longer need that. So we subtract it off, and let's move down here. We'll have E3 minus, and these projections get a little bit messier. We're going to have, it's not too bad here, 1/2, 1/2, -1, minus 21/58, -33/58, and -3/29. And if you work through all of the algebra, we end up with 4/29, 2/29, and 3/29. So our B prime orthogonal basis is going to be the set consisting of 1, 1, -2, -7/6, 11/6, 1/3, and our final vector here, the 4/29, 2/29, and 3/29. Again, this is an orthogonal basis for that same set, the same vector space, rather. And if we would like an orthonormal basis, then we'll simply take each of these vectors and divide by their norm. If you work through that, we end up with 1 over the square root of 6, 1 over the square root of 6, and -2 over the square root of 6 for our first vector. Take the second one and divide by its norm, and we end up with -7 over the square root of 174, 11 over the square root of 174, and 2 over the square root of 174. And finally, the third vector here, when we normalize it, we get 4 over the square root of 29, 2 over the square root of 29, and 3 over the square root of 29. So that would be an orthonormal basis for the same original vector space. And implementing that in Mathematica, we can define all of our vectors, set E1 prime equal to E1, compute the projection of E2 onto E1 prime, and then do the subtraction, get our first vector there, compute the other two projections, and then to create E3 prime, take E3 minus the projections of E3 onto E1 prime and E2 prime. And if we want to create an orthonormal basis, then we can use the normalize command in Mathematica on each of those. So the implementation in Mathematica is very straightforward, and you could program it as a loop and index the set of vectors and then go through and generate this with a sum. But if we're working in just 2 or 3 dimensions, then it may not be worth the additional effort and naming needed to get this set up to work. So that's the Gram Schmidt orthogonalization process.